Hi students, hope you all are doing good. As you know, we have started the chapter electric potential and capacitance, and last class, if you remember, we have discussed about potential energy, potential and potential difference, and we also spoke about the potential due to a point source charge and due to a dipole. Let us quickly revise once, okay? But before we revise, I want you to please memorize one small thing, and that is work done by any conservative force is always equals to minus of change in potential energy. So please memorize this. Okay, very important. Okay, a very simple way of understanding is, suppose a body goes from here to here. Okay, and let's say gravity, I want to calculate work done by gravity. Okay, so here let us say potential energy is initial is U1, final is U2. Understanding? And if I measure height from here, what will be U1? mg h1, and what will be U2? mg h2. h1 matlab this height, h2 matlab this height. Correct na? Okay. Now I am interested in work done by conservative force. Example of conservative force is gravitational force, electrostatic force, spring force. All these three are conservative force. Friction is not conservative force, remember it. So here, since I am moving a body against gravity, let us calculate what is the work done by gravity. So work done by gravity, small g here represents work done by gravity, which is this side. That is equals to force of gravity into displacement. Now I am moving the body up. So displacement is this much. Initial position to final position, that is your displacement. Gravity acts in what direction? Force of gravity is mg. In what direction it acts? Downwards. Correct na? Okay. So work done by gravity is mg, and cos theta also is there, no? So mg displacement is upwards, and what is the displacement? S. And in terms of height, if I write, what is this S? h2 minus h1. So S I can write h2 minus h1. And theta is how much? Theta is angle between force and displacement. Force of gravity is downwards, displacement is upwards. So angle is 180. Since angle is 180, cos of 180 is minus. Now look carefully. What is mgh2? mgh2 is the final potential energy, U2, minus mgh1. What is mgh1? Initial potential energy. So here you can see a nice example of work done by gravity is minus of change in potential energy. This is final potential energy minus initial potential energy. That will be change in potential energy. So this is something I want you to remember. I have done this previous to previous video also. So just to revise once, I am doing it. This is done in first PU also. So this is something I want you to remember, that work done by any conservative force is always minus of change in potential energy. This is always true. Okay, make a note. Always true. Always true. Okay, so keep this in your mind. Now let us discuss in electrostatics what happens. Okay, so imagine you have a source charge, which could be a point charge or any kind of charge. So this is a source charge, which means fixed. So let's say the value of the charge is capital Q. It could be point charge. If you remember last video, we have taken point charge. So any kind of charge you think, ring of charge, point charge, spherical charge, no problem. Now, if there is a source charge, you know at every point there will be some electric field. Correct? No? So if I put another charge, let us say small q, okay, then that charge will feel a force due to this source charge. That is your electrostatic force. If both are plus, it will be repulsive. This is your electrostatic force. Now, suppose you want to move this charge from position A to position B, let's say. You want to move this charge from A to B. The path is not important, okay, because it is conservative force. So it does not depend on path. You can come straight A to B, or you can go like this, like this, like this, and then you come to B, it doesn't matter. Now, if you come from here to here and you are saying you want to move the charge slowly, Slowly means you are not going to change the velocity. You are not going to accelerate. So kinetic energy should be constant. So no acceleration. Slowly means no acceleration. So the speed should be constant. So the kinetic energy should be constant. That means against this force, I have to apply some force. That is the external force. This is your external force. It could be Pankaj sir, for example. See, it is like earth is there. I want to move this duster from here to here against gravity. Then I have to apply some force. Whether upwards or downwards, it doesn't matter because I want to move it slowly. So if you want to move it slowly, you have to balance gravitational force. Here you have to balance this electrostatic force. So you will have to apply some force if you want to move the charge slowly. Now, try to remember work energy theorem. Work energy theorem says work done by all the forces is equals to change in kinetic energy. Here you are moving the body slowly, so change in kinetic energy will be zero because kinetic energy is constant because you are moving it slowly. So change in kinetic energy is zero. Now work done by all the forces means what? Work done by electric field plus work done by external force. Correct na? So work done by external force will be minus of work done by electric field. And since electric field or electrostatic force which comes from electric field is conservative force, just now I told you this will be always minus delta U. So this will become plus delta U. Okay. So work done by external force to move a charge from A to B against the electrostatic force is the change in electrostatic potential energy. Before we used to say gravitational potential energy, now we have to say electrostatic potential energy. But this is only true if we move the body slowly. If we move the body slowly. If we move the body slowly. Okay. So now this means the person who is applying force to this charge to move the body from A to B, to move the charge from A to B, he has to do some work, and that work done, how much I told it is equals to move the body from A to B, it is equals to change in potential energy. And change in potential energy I can write potential energy here minus potential energy here. So this is the very important definition of change in potential energy in terms of work done by external force. Suppose you want potential energy at this position, you don't want change in potential energy. Then if you remember what I told, you have to start from reference. And where we have chosen reference for potential energy? Infinity. So if I do work to move the charge from infinity to some point B, last class we took P. So this time I am writing B, and this will be what? Look at the formula and compare. It will be UB minus U infinity. And U infinity I am taking as 0 because that is the reference. Reference means wherever potential energy is 0. So potential energy at any position is equals to work done to move the charge by external force from infinity to that position. Now, after that we discuss one concept called potential. So in potential what we do, instead of moving charge Q, we move 1 coulomb charge. We move 1 coulomb charge, or you can say unit positive charge. So if you move unit positive charge, then the work that you do against the electrostatic force, that quantity we call potential. This is work done to move this Q charge. Okay. So keep in mind. So look carefully again. So to move Q charge, okay, whatever work is done is the potential energy. If you move from infinity to some point P, then that is potential energy at P. To move Q charge. If you move unit charge positive charge, matlab 1 coulomb. So Q is 1 coulomb. Then the work that you do is called potential. From where to where? Infinity to P. If you don't move from infinity to P, if you move from A to B, let's say, A to B, then you will get potential difference. But right now we are writing potential. So this is something I want you to know, students, very, very carefully, because later we have to solve many MCQs and all. So this will be important. Understood or not? So this is work done to move potential energy is work done to move Q charge. This is what is potential? Work done to move unit positive charge. Now how will these two be related? How will these two be related? Try to think. This is work done to move 1 coulomb charge. This is work done to move 1 coulomb charge from infinity to P. From infinity to P, this is work done to move 1 coulomb charge. To move 2 coulomb charge, how much work you will do? 2 into this. Yes or no? To move Q coulomb charge, how much work you will do? Q into this, and that is your potential energy. Understanding or not? So this is work done to move 1 coulomb charge. This will be work done to move Q coulomb charge, right? This is like price of 1 apple. This is price of 10 apples. So multiply with 10. So this is work done to move 1 coulomb charge. This is work done to move Q coulomb charge. And this is the relation between these two. Which means if I go back to the definition of change in potential energy. Okay, so if you do some work, the external force does some work to move the body from A to B. Then what I called this one? Change in potential energy. Remember, no? UB minus UA. Now use this definition here. What can I write? Q into VB minus Q into, this will be UB will be what? Q into VB minus Q into VA. So then if I take Q common, you will get VB minus VA. So this is the work done by the external force to move this charge Q from A to B. So please memorize this. Okay, very important definition. So in school, no, you may be remembering the definition of potential difference. You remember, right? In school. So if you look at potential difference, this is your potential at B. This is potential at A. So what is this? Potential difference. So what will be potential difference if you see carefully? It will be work done divided by this Q. Right? So this definition, if you see your class 10 textbooks in electricity chapter, current electricity chapter, you will find this definition. So this is potential difference, which is nothing but work done per unit charge, and it comes from here. And of course, this is work done from A to B by the external force. Against which force? What? Against electrostatic force. Okay, so please remember this, students. Again, I'm saying potential energy is work done to move Q charge, Q coulomb charge. Potential is work done to move 1 coulomb charge. Okay. Now, can you tell me, out of these two quantities, which one will depend on the source charge? Think for some time. What is capital U? Potential energy. What is capital V? Potential. Capital U is work done to move Q charge from infinity to some point. Capital V is work done to move 1 coulomb charge. So imagine here is your source charge, as I told in the beginning. This is capital Q. So from infinity to some point P I come. If I move Q charge, the work done is called potential energy. If I move Q charge. And if I bring from infinity to some point P, if I bring 1 coulomb charge, then that work done is a potential. Now out of these two, which one will depend on only source charge and not this charge? Can you think? Potential will depend only on source charge, because this is work done to bring 1 coulomb charge. This is work done to bring Q charge. Okay, so imagine like this. Imagine these are your Kashmiri apples. Kashmiri apples. and these are your normal apples. Normal apples. Okay. Now, if I ask price of one apple, that one will depend on only these two. No, it depends on the source, whether it is Kashmiri or it is normal. So price of one apple, if it is Kashmiri, it will be more. If it is normal apple, it will be less. Price of one apple. But price of some number of apples, that will depend on the number of apples also. You cannot say price of uh, some normal apples will be less than price of Kashmiri apples, or you cannot say price of some number of normal apples will be more like that, because suppose I take 100 normal apples and one Kashmiri apple, that doesn't mean Kashmiri apple will have more price. In that case, normal apple will have more price. Yes or no? So which one will have more price will also depend on number of apples. If you are asking price of many number of apples, but if you ask price of one apple, that will depend only on the source. Similarly, which one is work done to move 1 coulomb charge? This quantity, this is work done to move 1 coulomb charge. So this will depend only on source. This will depend on source also, and this Q also. How much Q you are taking, it will depend on that. It's like saying the price will depend on how many apples you take. But if you ask price of one apple, that will depend only on the source. So after talking about potential energy and potential last video, we also spoke about the potential due to a point charge. Okay, as I just now told you, potential will depend only on source charge. Potential energy will also depend on the charge which you are moving. Okay now students? Okay. So potential due to a point charge, point source charge, SOURCE. So if you have a source charge Q at a distance R, potential here P, let us say, that potential depends only on the source charge. If you call it capital Q, no problem. Then what was the formula? 1 by 4 pi epsilon naught capital Q by R. So this derivation, as I told, will come for 5 marks. We have done this already. Okay. And then for dipole, if you have minus Q charge plus Q charge separated by some distance 2a, and from center, if at a distance r at this point at some angle theta, if you want to know potential here, then it was 1 by 4 pi epsilon naught p cos theta by r square. P cos theta by r square. P was your dipole moment, which is either charge into distance between them. Okay. Then sometimes you can also see some books where they write this quantity this way. Look carefully. 1 by 4 pi epsilon naught. They write this quantity p bar dot r cap by r square. This is completely fine. Okay. What is r cap? A unit vector in this direction. Unit vector in the direction of this r, from center of the dipole to the observation point. So r cap is a unit vector from center of the dipole to the observation point. Now why we can write p cos theta this way? Let us try to see. How do you write a bar dot b bar? How do you write a bar dot b bar? Magnitude of a bar, magnitude of b bar, cos of angle between a bar and b bar, which is theta. So similarly, if I take p bar dot r cap, how will I write? Magnitude of p bar will be p. Magnitude of r cap is a unit vector, so magnitude will be 1 into cos of, what is the angle between p bar and r cap? P bar is taken from minus q to plus q, already you know. R cap is taken this way, from center to the observation point. So angle between these two is nothing but this theta itself. So I can write here cos theta, because this is the angle between p bar and r cap. So you can see p cos theta, which is here, can be written as p bar dot r cap. So in some books you may find this also. So try to remember this, especially for entrance. Okay, they may give you some options and this may be sitting there and you may think, Arey sir told p cos theta will be there, but here in the option p cos theta is not seen. That is because they are writing p cos theta in the form of dot product between dipole moment and this unit vector. Okay na? Okay, so now we will start a new topic today. So today we are going to discuss some very interesting topics. We will start with a topic called equipotential surface. Equipotential surface. Okay. So equipotential surface. Equipotential surface. So the definition of this is very common in your board exams. Okay. So what is equipotential surface? If I ask, as the name says, okay, it is a surface. It is a surface whose all points are at equal potential, are at same potential. That's right, same potential. So this is the meaning of equipotential surface. So it is a surface whose all points are at same potential. Okay, so keep this in mind. Now let us take for point charge plus q, let us take source charge plus q or capital Q, doesn't matter. Okay, right now. So at a distance r, what is the potential here? 1 by 4 pi epsilon naught q by r. What about at a distance r here? Here. Same it will be here. Same it will be here. Same it will be here. Same here. Same. As long as this distance r is same, potential also will be same. In other words, potential in this circle. So if I draw a circle with the source charge at the center, then every point will have same potential. So in that case, this is called your equipotential line because it is circle I draw. But you can draw a sphere also, no? So if you take a point charge, imagine this is your point charge and you take at a distance r, if you ask what is the potential, and then you make a sphere of radius r, then all the points will be at same potential. Okay. So for point charge, how will the potential equipotential surface look like? It will look like spheres with center as source charge. Okay, keep this in mind. Now we will look at properties of equipotential surface. Just like when we did electric field, we discussed about properties of electric field lines. Now we will talk about properties of equipotential surface. So if you remember 3 also, it is enough. Okay. So let us see properties of equipotential surface. Equipotential surface. So the first property is, listen carefully, work done to move a charge, any charge, okay, to move the work done to move a charge from one point to another point on the equipotential surface. On the which surface? Equipotential surface is 0. Work done to move a charge from one point to another point on what surface? Equipotential surface will always be 0. Let us think why now. What was the, in the beginning of this video I have given you one formula. Potential difference between A and B is work done to move some charge from B to A. Remember, no? A to B divided by Q. So if you remember this formula, you have seen this somewhere, right? Just in the beginning here, somewhere here I wrote. So check the video once. So this is the definition of potential difference. Potential difference between 2 points is work done to move this charge from B to A divided by that charge. So if you move from B to A, your change in potential energy. That time I think I wrote A to B. Yeah, I wrote A to B, and then I told you that will be equal to change in potential energy, right? If you move the charge slowly. So all those things I have done already. Let me not again and again revise. So this was from A to B, and this was VB minus VA. VB minus VA. Now look carefully. If A and B, okay, if you write this much in the exam, it is enough. I am giving you reason now why. Why work done will be zero if you move a charge from one point on equipotential surface to another point on the same equipotential surface. Then work done will be zero. But why? Because work done is given by this formula if you cross multiply, right? So work done from A to B will be what? Q into potential difference. Now if A and B, if the points A and B are on equipotential surface, if point A and B are on equipotential surface, then it means what? Potential of A must be equal to potential of B, because that is the definition of equipotential surface. All the points on the surface should be at same potential. So if A and B are on equipotential surface, then potential at A will be equal to potential at B. Therefore, work done to move any charge, it doesn't matter, will be Q into potential difference will be what? Zero, because those points are on same equipotential surface. So potential difference will be zero. If potential is constant, potential difference will be zero, na? So if potential difference is zero, work done will be zero. Okay, so this is the reason for writing this property. Let us now see the second property of equipotential surface. First property is work done to move a charge from one point to another point on the equipotential surface should be zero. Second property is, look carefully, electric field lines, those things that you have studied in the previous chapter, electric field lines are always perpendicular to equipotential surfaces. Equipotential surfaces. Okay, so keep this in mind again. Again, reason I will give, don't worry. So one of the best way to understand this is very simple. See, take a positive point charge. Positive point charge. Now just now I told how equipotential surface will look. Equipotential surface means a surface whose all points are at same potential. Now if you ask at some distance r, what is the potential? 1 by 4 pi epsilon naught q by r. 1 by 4 pi epsilon naught q by r. So at same distance from this charge, potential will be same. So if you draw a sphere, with the charge at the center, okay, with the charge at the center, potential everywhere will be same. So this will be your equipotential surface. Equipotential surface. For point charge I am taking, okay, equipotential surface. Now if you remember, how do you draw electric field lines? Radially outwards. So already now you can feel, right, this property you can see here. So you can see this is 90, this is 90, this is 90, this is 90. So electric field lines are always perpendicular to equipotential surface. So here in this, for point charge easily you can see. But in general, why it is true? Suppose you want to know why it is true in general. Okay, so look carefully. Imagine this is your equipotential surface. Equipotential surface. Okay. Again, reason and all is important for your understanding. For exam purpose, just remember this property. Now imagine this is your equipotential surface. Now think, electric field is not perpendicular, but suppose it is like this at some angle theta. Then you can divide this electric field into two components. From vector knowledge you know that, right? So this electric field will have one component parallel to the surface, and that will be your E cos theta. Which means if I take this point as A and this point as B, you can see that there is electric field from A to B. But if you remember my last video, I told you electric field is always from higher potential to lower potential. Rewind once and see. Electric field lines are always from higher potential to lower potential. So if there is electric field in this direction parallel to the surface, if there is electric field parallel to the surface, component of electric field is also electric field. No, component of apple will be apple only, not pineapple. So component of this electric field in this direction will be E cos theta, which is not zero. So if there is a component of electric field parallel to equipotential surface, then it means this potential should be greater than this potential, because electric field lines are what I told, higher potential to lower potential. But I know already I have explained to you that equipotential surface means what? These two should be equal. So potential of this point and this point should be equal. That means there cannot be any electric field here. There should be no electric field here. There should be no electric field parallel to the surface. Tangent to the surface, there should be no electric field. So if you don't want any E cos theta, what was this component? E cos theta. So you want E cos theta should be 0. That means E may be 0. Okay, no problem. But suppose electric field is there, suppose. Electric field is there, but you want this to be 0. Then what should happen? Cos theta should be 0. Cos theta should be 0 means theta should be how much? 90 degree. That means this electric field cannot be at this angle. How it has to be? It has to be perpendicular to the surface. Understanding or not, students? Correct now? Okay. So this is one very nice reason for understanding why electric field lines, if you do electric field lines, you can do no problem, should be perpendicular to the equipotential surface. If it is not perpendicular, then there will be a component parallel to the surface. And if there is a component parallel to the surface, then one point will be higher potential than the other point. But I know they are equipotential surface. So every point should be at same potential. Okay. So I hope you understood this. Let us see the third property now. So the third property says two equipotential surfaces cannot intersect. Third property, two equipotential surfaces. Two equipotential surfaces cannot intersect. So equipotential surfaces should not intersect. The reason, if you want to know, is very simple. Already you know. While teaching you electric field lines, I told you electric field lines cannot intersect. So if two surfaces, let's say this surface and this surface intersect, if they intersect, then what will happen? Just now previous topic what I told you, second property, electric field lines are perpendicular to equipotential surface. So for this surface there will be one electric field line like this, perpendicular to this surface, and there will be, for this surface there will be electric field line like this, and you can see electric field lines will intersect. But already we know electric field lines cannot intersect. That means even the surfaces should not intersect. Okay. Another property is that three properties are enough for your board exams. Another property we will do, but that we will do after doing one derivation. So let us do one very important derivation. In 3 marks it will come for exam. The question is relation between, derive the relation between electric field and potential. So we want a relation between electric field and potential. So what relation they have? Okay, so look carefully. So let us consider two closely spaced equipotential planes or surface, you can say. So this is one equipotential plane, this is another equipotential plane. Okay, so that means what? Every point here will be at same potential, and every point here will be at same potential. But those two will not be same, obviously. If those two were same, I would have made one surface only, no? So these are different surfaces. Understanding or not? See, it is like this. For point charge, for plus Q, how I told you equipotential surface will look like this, right? At some distance r, every point will be at same potential. What is the formula? 1 by 4 pi epsilon naught Q by r. Or suppose I draw one more equipotential surface. All these points will be also at same potential, but this will be lesser than this. No, if this is 5 volt everywhere, this will be 2 volt everywhere. Why it will be lesser? Because with increase in distance, potential due to positive charge should decrease, because it is inversely proportional to r. So this is one equipotential surface, this is another equipotential surface. So don't think this is also 5 volt, this is also 5 volt. Okay, so when I say 5 volt here, it means everywhere here is 5 volt. So similarly, you consider two equipotential planes which are closely spaced. So this is dx, let's say. This distance between them is quite small, dx. Okay. Now, how do you draw electric field lines? I told you perpendicular to equipotential surface. So electric field will be like this. Okay. Now, let us say this has potential V. Now, I have shown electric field line this way. That means this should be higher potential, this should be lower potential. Right? I have told you electric field is from higher potential to lower potential. So if electric field is this way, this should be higher potential, this should be lower potential. Sir, can't I show other way? You can show. If you draw this way, then here you should show higher potential, here you should show lower potential. That is up to you. So suppose electric field lines I am showing this way along your x-axis. This is your x-axis, let's say. Okay, so if electric field line is along your x-axis, that's why I wrote here dx, no? Then this will be higher potential, this will be lower potential. So if this is V, this will be V minus dV, where dV should be understood as positive number. So let me put modulus here, okay? Because it should be positive, because you don't want this to be negative. Then what will happen? Then this minus and this negative will make this positive, and therefore this will be greater than this. But already I have told you, if electric field line is this way, this should be higher potential, this should be lower potential. So what is the potential difference? Potential difference between the two surfaces is nothing but dV, right? Higher potential minus lower potential. So this minus this, if you do this, you will get. So that is your potential difference. Okay, now look carefully. Suppose I move 1 coulomb charge from here to here, from this surface to this surface, from A to B, against electric field, then that work done will be dW. Why dW? Because I am saying this distance is very small. So dW is the work done to move 1 coulomb charge from point A, which is in this surface, to point B, which is in this surface. So that work done will be, if you remember, force into this displacement. And if you remember, minus sign we write, because minus sign means what I have told you. Negative sign means work is done against the field. Work is done against the field. Against the field. Okay. Basically, it means your x is increasing this way. So your dx will be negative. So you want this to be minus, so that the dw is positive. Already we have done this while deriving the potential due to point charge. Please see once. So work done is force into displacement. Minus sign means, negative sign means work is done against the field. Okay, students, fine. Now, in this case, don't write force as 1 by 4 pi epsilon naught q by q1 q2 by r square, because I have shown you electric field and I have not told you the source charge of this electric field. It could be a point charge, it could be sheet of charge. The way I have shown, it is actually sheet of charge, because I have shown you uniform electric field. But forget about all those points right now. if there is electric field, how do you calculate force? Let me write this. Okay. So now, how do you write force on a charge Q? Let's say this charge is Q. How do you write force on this charge Q by some electric field? Q into E. Remember or not? This is the force on this charge by the electric field. And you also have to apply same force to move the charge against the field slowly, obviously. Okay. So when you do that, here I can write E. Why I can write E? Because Q is 1 coulomb. So if you substitute this here, what will you get? Let me write here. dW will be minus E dx. Now, by definition, what is this dW? Think carefully. By definition, what is dW? Work done. What kind of charge we are taking? 1 coulomb charge. That's why I wrote Q equals to 1. That's why F is equals to E. So I am taking 1 coulomb charge against the field. From where to where? A to B. That is what? That is potential difference. Remember or not? Work done to move a charge from A to B is nothing but potential difference between those 2 points. So this is nothing but potential difference, which already I wrote dV here. Understanding or not? See, go back to that definition. Work done by external force from A to B is Q into VB minus VA. Remember this definition in the starting only I have told. If you take 1 coulomb charge, then this is your potential difference. And that potential difference, in this case I wrote dV. And this work done I wrote dW. Why we are writing this way? Because we are taking for small distance. So dW is dV. That means if I substitute this here, what will I get? dV equals to minus E dx. So what will be E equals to? Minus dV by dx. So this will give you 3 marks. Sorry. So E will be equals to minus dV by dx. So if you are confused why I wrote dW as dV, then you see this thing which already I have explained. So work done by some external force to move this 1 coulomb charge from one point to another point against the electric field. That work done is nothing but potential difference, because this Q is 1 coulomb. If it was Q, then it will be Q into VB minus VA, I know already. Okay, so this is something that we have done already. Please check it out. So you saw just now I derived this formula between electric field and potential. So electric field is negative of dV by dx. And if you remember dV by dx, what is dV by dx? The rate of change of potential with respect to x. So some few important notes you make. First point, when we write this formula, okay, first if we write like this, then it means V is a function of only x, okay, and electric field is along x-axis. Electric field is along x-axis. So this is true for electric field along x-axis, and your potential is a function of x. That means as you move along x-axis, okay, your potential is changing. So this is 10 volt, this is 8 volt, this is 6 volt, like that. So as you move along this line, you see you are going from higher potential to lower potential. So electric field will be from higher potential to lower potential. Okay or not? So when I write this formula, it means potential is a function of only x coordinate, and electric field is only along x-axis. Now look carefully. If this is for your entrance actually, look carefully. If potential is a function of x also, y also, that means this is my x, this is my y, and when I move along x, that time also potential changes when I move along y, that time also potential changes. Then you know that in that case your electric field should be here also, here also. That means your total electric field will be somewhere here. So now your electric field will be not along x-axis. So then how to write electric field then in that case what we do is we write this formula this way. Ex will be minus this d we write as del v by del x. I will explain the meaning of this del little bit later, okay? So this Ex will be component of this E along x. Similarly, Ey will be minus del V by del y. And if there is Z also, then you can put Z also. Ez equals to also if you want. So this is how you have to find electric field components. See, it is very easy to understand. If potential is a function of x also and y also, for both syllabus, we just take potential as a function of x. That's it. But what if your potential is changing along x also, y also? Then there should be electric field along x, because if it is changing along x, then it means there will be higher potential and lower potential. So electric field will be this way. It could be higher here, lower here, higher potential here, lower potential here. Then electric field will be this way. Whichever be the case, there will be some electric field along x-axis. Similarly, if potential changes along y-axis, then there has to be some electric field along y-axis also. So then the resultant electric field will be somewhere here. So and these two will be only the components. So you have to find the components first by writing dv by dx formula only, but instead of d you have to write del. The meaning of del I will be explaining when we solve one problem, which is again only for entrance. So right now let us not discuss. So I will tell you the difference between del and d very soon. Don't worry, okay? And finally, how will you write electric field? Ex I cap plus Ey j cap. Correct na? So this will be your electric field. And then if somebody says find the magnitude, how will you find magnitude of a vector? Root over x component square plus y component square. You know this from your first PU, and we have done these things previously also. Okay. So these things I want you to know. Another point you see. So the second point, the second note is only for your entrance exams. Okay. Third point you say. Third note. Okay. If potential is constant, that means it is not a function of x coordinate also, y coordinate also, z coordinate also. Matlab you are moving along x-axis. Your coordinate is changing, but potential is not changing. Potential is constant. Then what will be electric field? Quickly tell me. If this is constant, then d constant by dx is 0. Then there cannot be electric field. Already we know that. No higher potential, no lower potential, all are equal potential. Then there cannot be any electric field. Okay. Second thing, this is the fourth point I think. Look carefully now. If let's say I have surfaces like this, equipotential surfaces like this. Okay, these are equipotential surfaces. Okay, so this has potential V1, so every point will be V1. This is potential V2, so every point will be V2. This is V3, every point will be V3. Now you look carefully. Listen to me carefully, okay? From here to here, if you go, and then from here to here, if you go. Listen carefully, I am saying. If you go from here to here, and then you go from here to here, potential difference will be same or not same. Potential difference. All these points are, see, all these surfaces, what I mean by this, what are these lines representing actually? These are equipotential lines, you can think. Or if you think in 3D this way, then you can think of it as equipotential surface. So these are equipotential surfaces. Okay, now listen carefully. These 2 points I took here, these 2 points I took here. So potential difference here will be what? V1 minus V2. Potential difference here will be what? V1 minus V2, because this is equipotential. So all points are V1. This is also equipotential. So all points are V2. Understood? Okay. So that means from here to here, here to here, dV is constant. Now this dx was what? The distance between the surfaces. That time I took plane surface. Remember here I am taking curved surface. So if I say, so A to B, here C to D. Now in which case the gap is small. This dx was the gap between the two surfaces. Rewind and see if you have forgotten. This dx. So this gap is small in this case. So if this gap is small, this E will be large in magnitude. Electric field is vector quantity, remember. So if somebody says tell me the magnitude, then you forget the minus sign. You just write the magnitude. Right? Okay. So if this dx number is less, this number will be large. That means electric field here, if I say is E1, here is E2, E1 will be larger because this gap is smaller. If the gap is smaller, electric field is larger. So from here students, you found one interesting property, and that is wherever equipotential surfaces are crowded matlab what? Closed. Electric field will be strong. Electric field will be stronger. So this is something very important. So I told you, no, I will give you one more property after doing the derivation. So one more property of equipotential surfaces are wherever the surfaces are close, electric field will be stronger. Now one last point, you see, they will ask sometimes the meaning of this minus sign. So negative sign in the above equation means, already we have told work is done against the field, but you can also say this way. Negative sign in the above equation means electric field is directed along decreasing potential. So basically this minus sign means as you move along x-axis, wherever the potential is decreasing, electric field will be in that direction. Matlab it will be from higher potential to lower potential. Already you know that. So the negative sign means electric field is from higher potential to lower potential. Instead of writing this part, you can also say from higher potential to lower potential. Same thing, because it is along decreasing potential. This is something very simple also. Okay, if you think of gravity, for Earth gravitational field is downwards, right? And if you know higher point will have higher potential energy, lower point will have lower potential energy. So even in case of gravity, the gravitational field is from higher potential to lower potential. So keep this in mind, very useful. Okay, then graphically, what does dy by dx represent? Graphically, what does dy by dx represent? So imagine this is your y, this is your x, and some graph I drew. Then what is the meaning of dy by dx in mathematics? You must be knowing already. So it represents the, if you at this point, if you want to know dy by dx, what you do? You have to draw a tangent to that curve at that point, and whatever angle it makes, that will be your tan of theta, and that all of you know is called slope. Slope of yx graph at that point, or slope of the tangent at that point. So if you know this, you can also write electric field is minus of slope of v versus x graph. Okay, or if you want to expand in words, you can write potential versus distance graph. Right, just like we used to have velocity time graph, right? And if you remember, slope of velocity time graph, dv by dt was what? Acceleration. Remember this first view. Slope of velocity time graph is dv by dt, which is nothing but acceleration. Similarly, this is your slope. So electric field is negative of slope of potential versus distance graph. So all this is again for your entrance. Let us now solve some learning exercise problems so that whatever knowledge you got, will remain with you. So the first learning exercise is learning exercise 2.2. Question number 1. Give an example of a point where potential is zero, but electric field is not zero. Already I have told you. So if you take a dipole minus q plus q, then at equatorial point, potential due to this charge will be 1 by 4 pi epsilon naught q by this r. And potential due to minus charge will be 1 by 4 pi epsilon naught minus q by r. Potential, remember, if charge is negative, potential is also negative. It's a scalar quantity. So if it is negative, it is negative. It is not like vector where you will say you are writing the magnitude. Okay. So potential here will be 0. But electric field at that equatorial point, you already know it's not 0. It has some value. This side. Already we have done this problem. Okay, last video. So example of this point would be where equatorial point of a dipole. Question number 2, you see the potential due to short dipole decreases faster or slower with increase in distance from the dipole as compared to potential due to point charge. So that already you know, potential due to point charge, single point charge if you take, then it is inversely proportional to distance. But potential due to dipole if you take, it was inversely proportional to square of distance. So it is very clear that potential due to dipole decreases faster. Potential due to dipole decreases faster. Why? Because r square increases faster, and r square is in the denominator compared to r square will increase faster. So 1 by increasing will be decreasing. It is inversely. So if this increases faster, this will decrease faster compared to this. Okay, fine. So this is completed. Now let us see exam corner 2.1. Exam corner 2.1. Exam corner, not entrance corner. Okay, exam corner 2.1. So the first question is, the electric potential is constant in a given region. Electric potential, capital V. Potential symbol is capital V. It is constant in a region, they are saying. What will be the electric field? What can you say about electric field? If potential is constant, you already know electric field is 0. So first question, answer is 0. Second question, in a certain 0.1 meter cube of space. So there is a space of volume 0.1 meter cube. They are saying electric potential is found to be 5 volt throughout. So throughout means everywhere in that volume, potential is 5 volt. What is the electric field in that region? If potential is everywhere 5 volt, means it is constant again. So electric field will be again 0. Third question. A uniform electric field exists between two charge plates. So one plate is here, imagine one plate is here. So these are two plates like this, plates. One is charged positively, they are saying. Diagram is also shown. And one is charged negatively. And there is a uniform electric field. Already we know sheets of charge produces uniform electric field. From our first chapter we know that. So they are asking you, what is the work done in moving a charge Q along the closed rectangular path ABCD? So there is a path ABCD. It is a closed path. What is the answer? Work done to move any charge from A to B to C to D to A. You are coming back to A now. So it is what kind of path? Closed path. And since they are asking work done, it will be 0 since electric field is conservative field, or electrostatic forces, you can write electrostatic force is conservative force. So since it is conservative force, work done must be 0 in closed path. One easy way. Another way is, see, when I go from here to here, electric field, I am moving in the direction of electric field. So from here to here, electric field will do positive work. From here to here, I am moving perpendicular to electric field, so no work. From C to D, I am moving opposite to electric field, so electric field will do negative work. From D to A, electric field will do no work because it is perpendicular. If displacement is perpendicular to force, work done is zero, na? And where is force? Force on a positive charge will be wherever there is electric field. Electric field and force will be in same direction. So electric field was shown by these red lines. So when I move from A to B, displacement is this side. Force is also that side. So work done will be positive. Here work done will be zero because perpendicular force and displacement are perpendicular. So work done will be zero. Here displacement is opposite to force. So work done by the electric field will be negative. Here again work done will be zero. So here positive work will cancel the negative work. But again, no need to think that way. Since it is conservative force, even if it was a closed path, work done will be zero. Okay. That is because electrostatic force is a conservative force. See question number 2 mark question now. For question number 1, you say figure A and B show field lines. Field lines means electric field lines of positive and negative point charge respectively. Very good question. Try to concentrate. Okay, please concentrate. So this is question number 1, 2 marks. Listen carefully. Here is a positive charge, and for point charge electric field will be radially outwards. Okay, let me draw some more. And one more, they have shown negative, they have shown this way. Even if they don't show, you know already. Okay, now listen carefully. One point is here P, another point is somewhere here Q. This is figure 1. Okay, in this figure point A is here, point B is here. These are just points. Okay, now listen carefully. First part, they're asking give the sign of potential difference Vp minus Vq. Sign they want. Vp minus Vq. Sign they want. Positive or negative they want. Now listen carefully. Just remember, electric field is always from higher potential to lower potential. So if it is positive charge, electric field is radially outwards. So electric field should be from higher potential to lower potential. That means Vp is greater than Vq. So if Vp is greater than Vq, Vp minus Vp is greater, na? So greater minus smaller will be positive. Easy, right? Okay. In the same part, they are also asking sign of Vb minus Va. Vb minus Va. Sign they want. Again, no need to think too much. Electric field line is this way, and electric field line is from higher potential to lower potential. So potential of B should be larger than potential of A. Some of you may get confused. Arey sir, B is far. If B is farther, then distance will be more, na? If distance is more, potential should be less. Please understand, potential is minus because charge is negative. So potential will be what? Minus 1 by 4 pi epsilon naught Q by R. So if R increases, usually we say this decreases, but minus sign is there. So if this increases, if this denominator increases, this number will decrease. I know that. And but minus decreasing means increasing. So this point will be higher potential. Again, don't think this way. Just think electric field lines are from higher potential to lower potential. And for negative charge, how do you draw electric field lines? Radially inwards. That means this is higher, this is lower. So Vp minus Va will be again positive. Ulta, if I ask, it will be negative, negative. Okay. Part B, now you concentrate. Part B. Give the sign. Again, they want sign of the work done by the field. Very carefully, they are saying work done by the field, not by the external force. Work done by the field in moving a small positive charge from Q to P. Now let us go back. Let us go back to the meaning. Here let me explain. Already I have explained, again let me explain. Work done by external force from A to B. How do we write? Q into VB minus VA. This is work done to move charge Q from point A to point B against the electric field. But if they want work done from A to B by electric field itself, that will be minus of this work done. Already I have told you, please revise and check. Okay, so be very careful. This is important. This is VB minus VA. Okay, this is something I've already explained. This is by external force. This is by electric field. It's like, see, when I move this duster up, I'm doing positive work, but gravity has to do negative work because I want to move this body slowly, na? That is the whole concept. So here they are asking work done by field. From where to where they told, let me revise, see once, from Q to P. How will you write? Since it's work done by the field, first formula or second formula? Second formula. So it is minus Q. A to B means VB minus VA, na? So Q to P means VP minus VQ. Now, they told what kind of charge they are moving? Positive charge. So Q is positive. VP minus VQ. Already we know is positive, so this is also positive. So this is positive, but minus sign is there. So so this left side will be what? Left side will be negative. So answer is negative. Part C, you see. Where shall I do part C? Let me do part C here. So this I hope everybody understood. Okay, now think. Same question if they had taken negative charge. Then this will be negative. This is positive. Minus minus will be plus. So be very careful. Part C they are saying work done by external agency. External agency means what? External force. Pankaj sir, you think? To move a small negative charge, remember, from B to A. So they want work done by external agency from B to A or A to B. Let me check once. B to A. First you write the formula. So external means first one or second one? First one. See, that's why I taught these things so many times before. Because these things for entrance questions and for this kind of conceptual questions, no, you should know this. Otherwise full confusion will be there. So work done by external force from B to A. How will I write? Q. A to B, how will we write? VB minus VA. So this is B to A. So how will I write? VA minus VB. Now look carefully. In the question, they told the charge which they are moving is negative. So this is negative. And this we have calculated, sorry, we have found here. See, VB minus VA is positive. So VA minus VB, ulta will be negative. So this is negative. If this is negative, this is negative. Negative into negative will be positive. So all we have answered, and this can be very much asked in your entrance exams also. Okay, so please make a note of this solution very carefully. Now let us see question number 2. So let us now see question number 2. It says two charges plus 2 microcoulomb and minus 2 microcoulomb are placed at points A and B 6 centimeter apart. So plus 2 microcoulomb and minus 2 microcoulomb, which is A and B, are separated by 6 centimeter. Basically it is a what system? Dipole. They want you to identify an equipotential surface of this system. Equipotential surface they want you to identify. Any one surface. So you know one point. See, if I ask potential here, equatorial point, what will be the potential? Already I have told here 0, because this distance is same as this distance, but this charge is positive, this charge is negative. So potential of the two potential due to the two charges, one will be positive and other will be equal negative number. It will be number only, it's a scalar quantity. So one is positive number, one is negative number. So when you do algebraic addition, you will get 0. So potential here is 0. What about here? So at every point in this line, it will be 0. So this will be your equipotential surface. So equipotential surface. Actually, it will be in 3D. If I show you, it will be like this surface. Okay. So if these are your charges A and B, then you can do a surface like this. Okay. So that all those points will be having same potential. How much? 0. And electric field, second part is what they are asking. The direction of electric field. What is the direction of electric field at every point on the surface? Already we know. Direction of electric field is always perpendicular to the surface. And if you go back and check electric field at this point, it was, due to plus it was away, due to minus it is towards, so total will be like this. So electric field, so part B is electric field is directed perpendicular to the surface. Which surface? This surface. Okay, fine. So now I will do, so this ends this session basically, but before we complete this session, some few things I wanted to tell you. So look carefully. Suppose let us do some small 2 marks problem, 2 marks numericals. So suppose I ask you question, if potential capital V varies with distance x given by some formula, let's say V equal to 2x power square, then find electric field at point. See, electric field is always found at a point, at point x equals to 2 meters suppose. So how will you answer this question? Since potential is given as a function of x, you know that as you move along x-axis, if this is your x-axis, if you move along x, this number will change, so potential will change. Any potential will change. There will be some higher potential, there will be some lower potential. So there will be electric field from higher potential to lower potential. What is the formula? Minus dV by dx. So it will be minus d by dx of this V. What is V? 2x square. And everybody, you are very smart in differentiation now. So 2 is constant, take it outside. Differentiation of x square will be 2x. So electric field will be minus 4x. So now at what point they want? X equals to 2 meters. So what will be electric field at x equals to 2 meters? Substitute here 2 meter. Minus 4 into 2. So electric field will be minus 8. Now unit what we used to write? Newton per coulomb. But now you can also write volt per meter. Either you write this way or this way. Now why this volt per meter? Check here. Electric field is also dV by dx. dV matlab potential difference, small potential difference when you go from one x to another x. And dx is the change in the x coordinate. Correct na? So this will be in volt. This will be in meter. So you can also write electric field unit now in volt per meter, whichever you want. So very simple question, right? So try one question yourself. Suppose V is 2x plus 5x cube and I want electric field at x equals to minus 1 meter. So this you try. Okay, so let me know the answer in the comment section. Please try, students. You are very good in differentiation now. I have come to know. So please do it. Okay. Now the question is, every time things will not be like that. Every time things will not be like this simple. Here what happened? Potential was changing with only x coordinate. So if I draw some figures, graphs to represent this change. So when I told you before potential is 2x square, it means if this is your x-axis, your potentials will look like this. Your potential surfaces will look like this. So for x equals to 1, at x equals to 1, this is x equal to 0, let's say, potential will be 2. So if all these points, whichever has x equal to 1, x equal to 1 is a surface now. So you draw a perpendicular surface, understanding or not? You draw a perpendicular to x-axis at x equals to 1. So everywhere your potential will be 2 volt. Then you say x equals to 2 meter. Okay, what will be your volt? Potential? Put 2 here, 2 square to 8 volt, like that. Understanding? Okay. So now your electric field will be now where? It will be you already know electric field is perpendicular to the surfaces, so it will be this way. Can you tell me why I made this way? Because it should be from higher potential to lower potential, and that is the meaning of that minus sign. Okay, fine. But again, I'm saying it may not be like this. Surfaces may not be like this all the time. What if your surfaces are like this? This is your x, this is your y, and surfaces are like this. This is 2 volt, let's say 10 volt, this is 5 volt, this is 0 volt, like that. Then your electric field will be now where? It has to be perpendicular to the surface, so it should be like this. So now you can see electric field will have x component also, y component also. So using that formula which I told, directly you cannot find. So you have to find x component first. Now you have to write del v by del x. Because now your v will be function of not only x but y also. Check. As I move this way along x-axis, if I move along x-axis, see my potential is changing. See 10, 5, 0. If I walk along y-axis, see 10, then here 5. No, because these lines, these are surfaces, no, like this. So I'll touch 10, then again I'll touch 5, then I'll touch 0. Understanding? When my surfaces was like this before, this is my x-axis. See, if I walk along y-axis, my potential is not changing, see, because all these points are same potential, 10 volt, 10 volt, 10 volt. If I walk only along x-axis, then potential was changing, 10, 5, 0. So in such cases, you have to do minus, I forgot, del v by del y. So this del, now I will try to explain what is the difference between d and del. So listen carefully. So let us say I am give you a question something like this. Potential equal to 2x square plus 3y x, like this. So let me put y here. What is there? Okay. So now you can see potential is function of x also, y also. So now if I want you to find electric field, if you find electric field at 2, 1 coordinate. Now I have to tell you x and y coordinate both. So if I ask such a question, then how will you do? First you find Ex. So Ex, how will you find? I told minus del V by del X. So substitute your x, v, 2x square y plus 3yx. Now when you take del differentiation with del, what you have to do is, if you take differentiation with respect to x, no, then you treat y as constant. You treat y as constant and do your normal differentiation. So what will be the normal differentiation if I take y constant? Directly let me do. So 2 and this y is constant will come outside. Differentiation of x square will give you what? 2x plus y you take constant, it will come outside. 3 is also constant outside. Differentiation of x with respect to x will give you what? 1. So your x coordinate will be 4xy plus 3y. That will be your x coordinate of electric field. Similarly, what will be your y component of electric field? Del v minus del v by del y. Now when you take this differentiation, you have to treat x as constant. Treat x as constant. So substitute the v function. V function was 2x square y plus 3yx, right? Okay, so now you have to treat x as constant. So minus first term, you see 2 will come out, x square will come out because x is constant. Derivative of y with respect to y will be 1, plus here x will come out, 3 will come out, differentiation of y with respect to y will be 1. So what will be the answer? 2x square plus 3x. So this is your ey and this is your ex. Now at which point they want? They want at 2 comma 1. At that point they want. So at that point what will be your ex? So just substitute, this is the x coordinate, this is the y coordinate, substitute it. So 4 into 2 into 1 plus 3 into y coordinate is 1. No, this is your y coordinate. No, this is your x coordinate, this is your y coordinate. So y coordinate is 1. So this will be minus, this is 8 plus 3, 11. Unit will be volt per meter. So Ex is minus 11. Similarly, tell me Ey, let me do it here, okay students, we don't have space. So Ey is minus 2 x square. What is x? 2. So 2 square plus 3 into x is 2. Okay, this is only for entrance, okay, this will not come for board exams. So this will be minus 4 into 2, 8 plus 6. Okay, this bracket I should put, na? Yes or no? No, no bracket because there is only minus here. This was minus, no? This is plus only, right? Oh, no. There was a bracket here, it should be. This is the bracket, na? Minus sign was here. So it will be bracket here. Here I did carefully, no? Minus, yes. So minus should be outside. Otherwise, see, minus 8 plus 6 will be wrong answer. Okay. So minus 8 plus 6. So that will be 40 volt per meter. So once you know the Ex and Ey, then what will be your total electric field? It will be root over Ex square plus Ey square. So then you can substitute and get the answer. Okay. So this is how you should find electric field if potential is function of x coordinate also, y coordinate also. So now the last topic we will do for today is to draw equipotential surfaces for different kind of charge distribution. We will not do all kinds of charge distribution, only 3 simple kind of charge distribution. So look carefully. The first one is point charge. So for point charge, how will you draw equipotential surface? Already you know, it should be concentric spheres. So these are your equipotential surfaces. Okay, so best thing is to draw sphere first and then draw the charge at the center. So this will be your equipotential surfaces. Okay, it will be spherical. If it is negative charge, also spherical. Only difference is if it is positive charge, if this is plus 10 volt, this is plus, with distance it will decrease, so plus 5 volt. If it is negative charge, it will be minus 10 volt, minus 5 volt. So minus 5 means it will increase. Okay. So for point charge, how will you draw? Spherical. Okay. Already I have explained to you. Then they may ask you for uniform electric field. For uniform electric field, how will you draw equipotential surfaces? Now first you think, how do you draw uniform electric field? Like this you draw or not? So if your electric field is uniform like this, how should be your surfaces? The clue is electric field lines are perpendicular to equipotential surface. So your surface should be perpendicular to these lines, like this. So this will be your equipotential surfaces. Now sometimes we don't draw planes, we just draw, if this is the electric field line, we just draw these lines. Okay, matlab, if this is the surface, if you see from this side, you will see only line, no? This part you will see, so this part we are showing. Okay, so either you can show this way or you can show this way. Then they will ask you for dipole. How will you draw equipotential surface for dipole? So look carefully for electric dipole. See, we are trying to draw equipotential surfaces. Okay. So for dipole, how will we do? So imagine this is your plus Q and this is your minus Q. First thing is try to remember how electric field lines look like. That will help you to draw equipotential surface. So if you go back to our first chapter, electric field lines look like this. Let me use black color. Okay. So this is how it looks. Remember, right? Here it looks away like this. It looks towards, then away, away, then it will look towards, right? Okay. So it goes something like this, right? Already I've explained to you. So if this is your electric field lines, how will you draw equipotential surface? Very simple. Try to draw perpendicular to these lines. So here it is very easy. Perpendicular will be like this. Now here how will you draw perpendicular? See, this is perpendicular. No, 90 degree to this line. 90 degree, 90 degree, 90 degree, 90 degree. You're understanding or not? You have to draw equipotential surface perpendicular to the electric field lines. So this is your electric field line. Electric field line. You have to draw perpendicular. So it will be something like this. Then as you come closer, it will become like this. Okay. Then you have to draw here perpendicular like this. Then very close, it will be circle only. Because very close. If you are very close to this charge, then this charge doesn't matter. No? Then it will look like spheres. Then it will look like this. Okay. So you can see here the lines will be grounded compared to here. This they will not ask you to draw, don't worry. But since it is there in textbook, I wanted to show you. Okay. Same thing you have to draw here. So you draw a sphere here, then you draw a sphere like this, then you draw something like this. Okay, like this. So basically it should be perpendicular to the lines. Okay. So these are your equipotential surfaces. If you are not able to draw this, no problem, students. But at least in MCQs, if they show you options, you should be able to tick. Similarly, for plus charge, if they ask, how will you draw? If you remember for plus charge, if you remember here, there was no electric field line. Remember? No? Okay. So it was something like this. It is away, away. Then it goes like this. Then it goes something like this, right? So this was your electric field lines. Now you have to do perpendicular. So perpendicular, like this you think. So it will look something like this. Perpendicular, perpendicular will come down. Then again perpendicular up. Perpendicular like this, something like this. Okay. Should be up, no? Because it should be perpendicular. See, perpendicular to this will be like this, but perpendicular to this should be like this, no? So the graph has to go up. The surface has to go slightly up and again down and like this. So like this you draw some multiple ones like this. Okay, something like that. In your EPL the graph is there, but again they will not ask you to draw this in your board exams, but in MCQ if you see the graphs you should be able to, figures, diagrams, you should be able to tick the right one. So this is for your dipole, very important, and this is for your positive charge. Okay, so we'll stop for today. Hope you understood it nicely. Please try to revise whatever has been done. Again and again I keep saying that is very important. Revision is the only way to remember things properly. Okay, see you next class.